Good morning, one and all. Myself, Nagajyothi, working as an assistant professor in Department of ECE in Mlritm College. So, today I am here to discuss about a topic in case of control systems. In previous lectures, we have discussed about the basic overview of the control systems and what is meant by a control system, classification of control systems, that is of open loop as well as closed loop control system. In case of closed loop control system, we are having positive feedback as well as negative feedback. Again, this positive and negative feedback has been classified into unity feedback as well as non-unity. So based on the closed loop system, in which there are different parameters are going to be affected. So how gain, sensitivity and noise is going to be affected, all those things we have discussed in the previous lecture. So today I am here to discuss about how to represent a control system in a mathematical modeling. So in case of control systems, we are using a mathematical modeling representation, in which in this session I am going to discuss about how to represent a control system in a mathematical representation and what are the different types of mathematical models and how to represent an electrical system in case of a mathematical model. And for this electrical system, how to calculate or how to find out a transfer function for a given electrical network. So in this present lecture, I am going to discuss about representation of a control system in a mathematical model, and from among this mathematical model, I am interested to discuss about how to represent an electrical system transfer function representation. So what is meant by a mathematical model and why we are using this mathematical model? So basically, a mathematical representation helps in the analysis of a system. So if we take any system, how to analyze the given system is very simple if we are going for the mathematical representation. And by using this mathematical representation model, we are able to capture the dynamics of a system. So capturing the dynamic of a system itself indicates variations of the different parameters from time to time can be done or can be captured with the help of a mathematical representation. So the best examples for a mathematical representation of a system is, in case of an AC, whenever we are switching on AC, we can able to see what will be the change in the room temperature. So in this case, dynamic change of a system represents from time to time how the temperature of a room is going to be changed whenever the AC is switched on. Similarly, how can we see the change of the speed of the car when an accelerator is pushed by certain angle? So whenever we are driving a car, whenever an accelerator is pushed, how the speed can be changed in a car can be represented or can be understood easily by representing in a mathematical form. Or the third example is the current flowing through an inductor when an AC voltage is applied. So whenever we are taking an electrical circuit, basically the elements which are present in an electrical network is a resistor, capacitor and an inductor. So in this example, I am saying that how the variations in the current can be seen in an AC voltage. So generally we will be taking a plant or a system. This plant or a system here we are going to represent in a mathematical manner. So basically there are three types of mathematical model. The first one is a differential equation model, second one is a transfer function model, and the third one is a state space model. So when we are using each one, basically this differential equation model is used whenever we are representing a time domain representation of a system. So whenever we are representing a particular system in case of a time domain analysis, generally we'll go for the differential equation model. And by using this differential model equation, you can easily able to write down a differential equation. Coming to the transfer function model, if you want to represent a system in case of a frequency domain representation, we'll be using a transfer function model. And in case of a transfer function model, we'll be using a Laplace transform expressions. And coming to the third model, which is nothing but a state space model. In case of a state space model, we'll be using a set of variables which will give you the relation between the input variables and the output variables. And in case of a state space model also, we are representing with the help of a differential equations. So the main aim, or what are the different types of a mathematical models are three types. One is a differential equation model, second is a transfer function model, and the third one is a state space model. So in case of a differential equation, we'll be using a time domain representation, and which will be used as differential equation. But whereas in case of a transfer function model, instead of using a time domain representation, we'll be using a frequency domain representation, which is represented in terms of a S-plane. So here basically, in case of unit 1, we are completely dealing with a transfer function model. So before going for the transfer function model, first of all, we must know what is meant by a transfer function. So the transfer function is defined as a ratio of Laplace transform of output to Laplace transform of input, assuming the initial conditions as 0. So what is the meaning of this is nothing but, if you take any system, you are representing as ratio of output to input. As I told you that if you consider any electrical network in which it consists of R, L and C components, let me take the input voltage is Vi, and this is a resistor R, inductor followed by the capacitor. So if you see this circuit, among this circuit, as there are three elements, among these three elements, inductor and capacitor, we know that these two are the energy storage elements, which will store the energy in the form of either in the electric field or in the terms of magnetic field. So whenever I'm applying an input voltage, already there will be some sort of charge present in the inductance and capacitance. But whenever we are analyzing by using a transfer function model, we are assuming that the assumption is in such a way that the energy stored in the L and C component should be 0. So the main limitation of a transfer function model is whatever the energy which was present previously stored, that should be assumed as 0. In order to avoid this drawback, we are going for the next model, which is nothing but a state space model, in which we are considering the energy stored is also considering while calculating the transfer function. Coming to this, so how can you represent a mathematical model in all these cases? So here I am assuming that I have taken a simple RLC network. The input voltage is V and the current flowing through the circuit is I. So in this case, if we are representing in terms of a differential equation, that is nothing but called as a differential equation model, and if you are representing in terms of S domain, it is nothing but called as a transfer function model, and if you are representing in terms of matrix notation, then it is nothing but called as a state space model. So the complete first unit deals with the first two types of equations. One is nothing but a differential equation model and the other one is a transfer function model. As I told you, the drawback of transfer function model is the assumption is initial conditions are assumed to be 0. In order to avoid that, we will be going for the state space model, which we are going to discuss in case of module 5. So here the first thing is, how will you represent this in case of a differential equation model? So the first, I am representing an equation in such a way that the applied input voltage Vi of t is nothing but, as we know that I is equal and V equal to I into R. So voltage Vi of t equal to current flowing through the circuit is I of t, and as it is the first element is R into I of t, plus voltage across the inductor is represented as L into di by dt, and output we are taking across the capacitor, that is V naught of t equal to 1 by C integral I of t dt. So instead of representing it as 1 by C integral I of t dt, here I am representing it as V naught of t, and this I of t is nothing but, if you differentiate this, you will be getting that C into dV naught of dt. So from these two equations, if you are replacing this I of t here, this is R, substitute this equation 2 in the equation 1, Vi of t equal to R into I of t is nothing but C into dV naught by dt, plus di by dt is nothing but differentiation of I of t with respect to that of V naught of t. So if you expand this, you will be getting dV naught by dt into RC, d square V naught of dt by dt plus V naught of square. So Vi of t equal to RC into dV naught by dt plus LC d square V naught of dt plus V naught of t. And rearranging this equation will give you, first I am writing this d square V naught of dt, and I am dividing this complete equation with L, so that becomes R by L dV naught by dt plus 1 by c. So if you observe this, it consists of a second order differential equation. So this representation is nothing but called as a differential equation model. So in case of a differential equation model, we're representing the complete circuit in terms of current equation, and we'll be representing an equation model. So here the next model is nothing but a transfer function model. As I told you, in case of a transfer function model, I need to represent the complete equation in terms of S. That is nothing but transfer function is Laplace transform of output by Laplace transform of input, assuming the initial conditions as 0. So whenever I am performing Laplace transform, the basic things which I required is, now if x of t, the Laplace transform of x of t is nothing but x of s. Similarly, d by dt of x of t, Laplace transform is nothing but s into x of s. Laplace transform of d square dt square x of t is nothing but s square into x of s. Whatever may be the three conditions which we are considering, all these three conditions, the initial value is assumed to be 0. So what is the meaning? If it is a single differentiation, the Laplace transform is s into that input variable. Similarly, if it is double differentiation, s square into that input variable. If there is no differentiation term, which is nothing but x of s. So these are the three things which you need to remember while solving the expression for the transfer function model. So if you observe, the first thing is, whenever we are solving for the transfer function model, already from the previous one, the same example here I have taken, that is a simple RLC network, from which I have written an expression in terms of an output and an input voltage. Now apply the Laplace transform. For this equation 3, if you apply as it is d square by dt square, which is nothing but an s square, V naught of t is nothing but V naught of s, R by L is a constant representing in the same way, dV naught by single differentiation is capital S, which is nothing but V naught of S, plus 1 by LC V naught of S equal to 1 by LC Vi of S. So for the given differential equation, applying a Laplace transform will give you the transfer function model. Now in this, as I told you, that a transfer function is nothing but a ratio of output to input, rearranging the same equation. So here the equation is s square V naught of s. I am taking V naught of s as common. If you take V naught of s as common, the first term is s square, the second term is R by L into s, and the third term is 1 by LC. Here also you are having a 1 by LC Vi of s. Taking this Vi of s to term to this side. So V naught of s by Vi of s will give you 1 by, if you cross multiply and simplify this, you will be getting s square LC plus SRC plus 1 by LC. So this is a transfer function model in which the overall transfer function for a given RLC network is I by S square LC plus SRC plus 1. The same thing I can represent in another approach. In the previous example, first I have written the expression in a differential equation model, then I have applied the Laplace transform, then I have got an expression for the transfer function. Instead of doing that way, I am representing the same circuit in such a way that I am redrawing this RLC. So let me assume that this is Vi of t, R, L, C, and the current flowing through this circuit is I. So the first thing is, I need to, as we know that the Ohm's law is V equal to I into R, the first thing is I need to represent an expression in terms of output voltage. So V naught equal to, the current flowing through this circuit is I, and Here the output you are taking across the capacitance. And please remember the other more important thing, as I am performing a transfer function model in which is nothing but in a frequency domain. So here capacitance is nothing but 1 by 2 pi fc, which is nothing but omega c. This can be written as 1 by sc in case of Laplace domain. So here instead of c, I need to replace with 1 by sc. Similarly, inductance is 2 pi f into L, which is nothing but omega L. This is nothing but SL. So as I am using a transfer function model, which I am directly representing in a Laplace form, the output, that is output is taking across the capacitance. So 1 by SC. Make it as an equation 1. Similarly, I need to write down the expression for the input voltage. VI equal to I into total resistance in the circuit or total impedance of a circuit, R plus SL plus 1 by SC. From this, I can represent it as SCR plus S square LC plus 1 by SC. From this, take the equation in such a way that represent in terms of I. That is VI by S square LC plus SCR plus 1 by SC. This can be represented as VI by 1 into SC S square LC plus SCR plus 1. This is an expression for I. Make it as an equation 2. Substitute this equation 2 in equation 1. Substituting 2 in 1. So V naught equal to, what is I expression? VI by 1 into SC by S square LC plus SCR plus 1 into 1 by SC. This SC will be cancelled out, and we are getting an expression in such a way that V naught equal to VI by S square LC plus SCR plus 1. But what is the transfer function? Output. What is output? V naught. What is input? Vi. So V naught by Vi, which is nothing but 1 by S square LC plus SCR plus 1. This is a transfer function for a given electrical network of an RLC circuit. This is how to find out a transfer function for a given electrical circuit. Now, so as I told you that a basic electrical circuit consists of 3 elements. One is resistance. It is an element which resists the flow of current, and according to the Ohm's law, we are representing it as V equal to IR, or I equal to V by R, or R equal to V by I. And inductance, which stores the energy in the form of a magnetic field, and capacitor, which stores the energy in the form of an electric field. As already I have told you, this is a representation. For the capacitance, you are representing it as 1 by SC. For the inductor, you are representing it as SL. And for the capacitor, we are representing it as R. So, for the same circuit, see, let me take how to find out a transfer function for this given network. So if you observe this circuit consists of only two things. One is R and the other one is C. So here we are taking the output across the capacitance. So the first expression is V naught equal to the current flowing through the circuit is I, and output is taken across the capacitor. So I into 1 by SC. Similarly, the second thing is we need to write down the input expression or input voltage. So Vi equal to I into current flowing through the complete circuit. The elements present in the circuit is R and C. So R plus 1 by SC, which can be written as SCR plus 1 by SC. So here Vi equal to I into SCR plus 1 by SC. But I want from this expression the equation of I, which is nothing but Vi by SCR plus 1 by SC, which can be written as Vi by 1 into SC by SCR plus 1. Now substitute, make this as equation 2 and substitute the equation of I in terms of in equation 1. So substituting that V naught, instead of I need to replace as Vi by 1 into SC by SCR plus 1 into 1 by SC. This SC will be cancelled out. If you take this V naught term to this side, we'll be getting V naught of by Vi, which is nothing but 1 plus SCR. That itself indicates this is a transfer function. Now if you observe this in the given circuit, and for this one, from if you are equating this numerator part of a transfer function to 0, it will give you the zeros of a system. Similarly, if you equate the denominator part of a 0, it will give you poles of a system. The complete stability of a control system depends upon the location of the poles. So, in case of a numerator part, as there is no S term, there are no zeros. But whereas in case of a denominator part, there is a term which is nothing but 1 plus SCR. Equate this 1 plus SCR equal to 0, that is SCR equal to minus 1, S equal to minus 1 by RC. That itself indicates there is one pole present at minus 1 by RC, and the exact location of pole depends upon the R and C values. So what is the conclusion of this point is, the number of energy storage elements present in the circuit will give you the number of poles. It will not specify where the exact location of pole, but you can say how many number of poles are present in the circuit. So as the circuit consists of a single energy storage element, which is C, so the number of poles in the circuit is nothing but minus 1 by RC, and this is the pole 0 plot. Pole is present at minus 1 by RC. This is the pole 0 plot for a simple RC network. Similarly, the next example is finding out a transfer function for a given RL network. As usual, the first thing is representing the complete expression in terms of an output voltage. The current flowing through this circuit is I. V naught equal to I into SL. And the input voltage Vi equal to I into total impedance of a circuit R plus SL. Make it as equation 1. Represent this in terms of I, R plus SL. Make it as equation 2. Substitute 2 in 1, that is V naught equal to Vi by R plus SL into SL. Make this to the other side, that is taking this V naught by Vi, it will give you SL by, this is R plus SL. So this is the transfer function for the given. If you observe here, numerator part, if you are making numerator part to 0, SL equal to 0, that itself indicates S equal to 0. Making this denominator part as also 0, R plus SL equal to 0, SL equal to minus R, S equal to minus R by L. This itself indicates a pole 0 plot consists of a 0, and a 0 is present at where? Origin, and zeros are represented with a circle. So a 0 is present at an origin, and other more pole is present, and that pole is located at minus R by L. So this is a pole 0 plot for an RL network. And as I told you previously, in this case also there is only one storage element, so it consists of a single pole, and where that pole is present, it is present at minus R by L. So number of poles will depend upon the number of storage elements in the circuit. This already we have seen in the previous case, that is output is taken across the capacitor V naught equal to I into 1 by SC, Vi equal to I into R plus SL plus 1 by SC, and this can be written as SCR plus S square LC plus 1 by SC into I. I can be written as Vi by 1 into SC S square LC plus SCR plus 1. Substitute this I equation in terms of 1. V naught equal to Vi by 1 SC by S square LC plus SRC plus 1 into 1 by SC. This will be cancelled out. If you take this, we'll be getting a transfer function in which I'll be getting S square LC plus SCR plus 1. So in this, it consists of two energy storage elements. One is L and the other one is C. That is the reason here I got the term as S square. That itself indicates there are two poles present. As it is a denominator part, equating this denominator part will give you the poles. The number of poles are 2 and the location of the poles depends upon the R, L and C values. Thank you.